In this video, I'm going to be performing a von Neumann stability analysis like I did in part 3 of this video playlist, but this time I'm going to be doing it on the Crank-Nicholson method that we used in part 4 to solve this problem. So here's the equation that we used in the last part to get the temperature profile of the bar. And then I also wrote down the solution to the heat diffusion equation for this problem. So I talked a little bit about it in part 3 of this video playlist, but basically this solution is valid for our heat diffusion equation for all values of K. And I'm going to go ahead and plug it into this equation and then use it to show why we can use any value for K and delta T in the Crank-Nicholson method. So the first thing I'm going to do is I'm going to, on the left side, factor out a Tj at n plus 1. And then use this expression to kind of, or work this expression in and rewrite the left side of this equation. So to factor it out, I'm just going to write it over here. And then for our first term, we have negative u. And then Tj plus 1 differs from Tj by a factor of 1. So using this equation to account for that, we need e to the I k of j plus 1 delta x times e to the negative alpha k squared of n delta t. And so all we have to do to get from here to here is multiply by e to the I k delta x. And that'll increment by 1 power, and so we'll have j plus 1 in the exponent. So coming back over here, all we have to do is multiply by e to the I k delta x. And then here we have the right increments, so we just need to write out that factor, which is 1 plus 2u. And then we have negative u, and in this term, it's j minus 1. So to get that, we just have to have negative I k delta x. Ooh, I'm going to go ahead and get rid of this work so it's a little easier to see. And then we're going to do the same thing for the right side of the equation. So this is equal to, for the right side, we're not at the next time increment, we're at the previous time increment n. So I'm going to pull that out and then do the same thing. We have u times the temperature at j plus 1. And so to get the j plus 1, we'll just multiply by e the I k delta x. We just have for the middle term just the factor of 1 minus 2u. And then for the last term, we're at the previous increment. So it's going to be u times e to the negative I k delta x. And so this expression's already started to clean up a little bit. Now I'm going to apply Euler's method, or Euler's formula. And it's that e to the I k delta x is just equal to the cosine of k delta x plus I sine of k delta x. And so when we have this, and we also have e to the negative I k delta x, which the cosine, the sign does not change, but then it becomes minus I sine of k delta x. And when we add these two values together, the I times sine will cancel out, and we'll just be left with 2 cosine of k delta x. And so for the left side of the equation, we have both of these terms, e to the I k delta x and e to the negative I k delta x, and we also have that for the right side of the equation. So I can go ahead and substitute both of these in. and it'll simplify our equation a little bit more. So for the left side, we'll have the 1 plus 2u, and then since these are both negative, we'll have minus 2 from Euler's formula times u times the cosine of k delta x. And that's going to be equal to the right side, which is tj at n, and we can go ahead and do the same thing. So we'll have 1 minus 2u plus cosine plus 2u times the cosine of k delta x. And so from here, I want to isolate this term because that was the term we were looking for in the problem. It's the temperature at J at the next time increment. So to do that, we just need to divide by this term here. And this is what our equation looks like now. So now we can start to think of it like we did in part 3 of this playlist. Think of this as a geometric sequence. And so if this value, if the absolute value of this term is greater than 1, then that's when we have issues and the temperature on the left-hand side goes to infinity. And so I'm going to go ahead and simplify this equation a little bit further and kind of talk about why this value will never be greater than 1. So to simplify it a little bit more, we can go ahead and combine these like u terms. So for the top, we're going to have 1 minus 2u times, we'll have 1 plus cosine and then in the bottom, we'll have 1 plus 2u times 1 minus cosine. So I made a little bit of a sign error when I combined terms. I went ahead and fixed it. So the expression now looks like this. We have 1 plus 2u times cosine of k delta x minus 1 over 1 plus 2u times 1 minus cosine of k delta x. Now from here, I'm going to go ahead and multiply the top by -1. So switch this sign to a negative and we'll be able to flip the cosine -1 term so it looks a little bit more like the term on the bottom. So it becomes 1 minus 2u times 1 minus cosine of k delta x over, and then the denominator doesn't change, it's still 1 plus 2u times 1 minus cosine of k delta x. And now we can kind of take a look at the value of what cosine is going to be. So u is always going to be a positive number. It's a function of delta t, delta x, and k, and all those values are positive. And then cosine has a range of values between 1 and -1, And so this term here will always be greater than 0. And so if we write this fraction and think about it just as any number, like w, and w is always greater than equal to 0, then if we take 1 minus a number that's greater than 0 and divide it by 1 plus a number that's greater than 0, the denominator will always be a larger term, and so this whole expression will always be less than 1. And so because it's always less than 1, our temperature at the next time won't keep getting larger and larger and end up at infinity. And so this method is stable, and that's why we were able to use any value of k and any value of delta t in our code.